students, welcome back. This is Torres, elbow bump. How are you? Are you doing okay? How's your family? Are they okay? Remember, if you need anything, please send me an email and I'm happy to help in whatever way I can. So lucky you get to hear my voice for another lecture. But the best part is we will be comparing two population proportions with confidence intervals. Yay! Let's do a really quick review. Remember, the parameter is the statistic of the population. The parameter holds the truth. A lot of the times, we cannot know what the truth is because we don't have access to the whole population. So we have to take a sample and use the sample to learn about the population. We understand that because the sample is just a small piece of the population, we will have some level of error. In order to try to account for that error, a confidence interval allows us to provide a range of plausible values for the population parameter. In other words, we can say we estimate that the proportion of the population is this blue value. But we want to be truthful in that we understand there's some level of error in this calculation because we didn't have access to everybody in the population. Therefore, we can say with some degree of confidence that we expect the true population to exist within this lower bound and this upper bound. This is what we think it is. We know there's some level of error. So accounting for that error, we believe with some level of confidence it exists between this lower level and this upper level. As you increase the confidence of which you can state that range, the width of the confidence level also has to increase. And some commonly used values are 68, 95, 99, which, if you recall, are what we started talking about many chapters ago, many lectures ago, right? When we talked about how the distribution, if you have a normal distribution, approximately 68% of the values will exist within one standard deviation before and after the mean, or if you're working with proportions, the proportion. 95 will exist within 2 standard deviations of the center value, the proportion or the mean. And within 3 standard deviations, 99% of the values will exist. And this happens every time you have a normal distribution. That's why we want to check over and over if we can apply what we know about the normal distribution. When we calculate the confidence interval, we are looking to find this very precise z-score for the level of confidence, and that is called the ZScore Multiplier. And we're going to multiply it by the standard error of our sample. If we have a large sample, the standard error will be less. If we have a small sample, the standard error will be more. In order for any of this to be true, we have to meet the assumption of normality, either by checking the descriptive statistics and figures ourselves, or by being able to apply what we know about the central limit theorem to assume normality. The z-score multipliers for various confidence levels are in the description box below. There's a table in the description box below. We use these specific multipliers instead of the general ones we did when we first started looking at the empirical rule because we're trying to increase precision and therefore lower the quantity of error that is built into the calculations. So now that I've reminded everyone about the benefits of having the normal distribution, let's see how we can use those benefits to compare 2 different samples. So let's look at this. So a sample was taken using simple random sampling, SRS, of 100 students from school 1, and a completely separate sample was taken using SRS, that's simple random sampling, of 200 students from a different school, school 2. The proportion of girls was calculated. So they figured out what percent of the sample is girls. So let's see what they did here for school 1. Here they took 1,000 samples using simple random sampling of 100 students, and they plotted the percentages that were girls. So they took 100 students, they counted up how many were girls, figured out the proportion, plotted it. Took another 100 students, figure out what percentage were girls, figured out the percentage, plotted it. Kept doing that 1,000 times. For the other school, they did the same thing. This is called bootstrapping, when you do things over and over again. They took, this time with school 2, they took 200 students, calculated what proportion were girls, and plotted it. Then took another 200 students from school 2, figured out what proportion were girls, and plotted it. And they did that 1,000 times. So they took 1,000 samples of 100 students from school 1, calculated the proportion, and plotted it. They did the same thing with school 2, 1,000 samples, but this time they took 200 students from each sample and plotted it. Okay? They figured out the standard error here, and they could see that this was the normal distribution. Okay, the center value was 0.7, calculated the standard error, did the same thing here. They found that the proportion, that was the mean proportion, was 50. They calculated it here and figured out the standard error. Okay, so this is all the information for school 1, all the information for school 2. We wanted to compare the two schools. So what they did is they took the percent girls from school 1, which is 70%. That's the average percentage of all the different samples. They took the average percentage proportion of the girls in school 2, which was 50%, and they subtracted it. So 0.7 minus 0.5 is 0.2. So the new center here is going to be 0.2. So see, 0.7 minus 0.5 is 0.2. So now we have a new mean. They did that for all of those samples. So here they had a normal distribution, school 1. School 2 had a normal distribution. And then when they took the difference of school 1 and school 2, they also got a normal distribution. And they were able to figure out that standard error as well. Okay, so the big takeaway here is if you have one sample, regardless of of the sample size, and you can assume that distribution is normal, and you have a different sample, doesn't matter what the sample size is, and you are able to apply the idea that that distribution is normal, then you can take the differences of the two, and those differences will also be normal. And you can find the new center by subtracting the mean values from one another to find a new mean value. And you can also calculate the spread with a different standard error formula. So what we're going to do is we're going to take information about proportions for two different samples, the proportion for sample 1 and the proportion for sample 2, and we're going to take the difference of those two. That statistic will allow us to estimate the difference between two population proportions. So we'll be able to make inferences about the comparison of two populations proportions by comparing the two sample proportions. Now, think of it this way. What does it mean when there's no difference? If you have two numbers, let's just say 5 and 5, you know there's no difference between those numbers because if you take 5 and you subtract 5, what are you going to get? 0. To say that there's no difference between a proportion of one sample and the other is to say that there is 0 difference. And I'm pointing out the number 0 because I want you to remember, goes back way back to when you were little. 0 difference means no difference. 0 difference means no difference. So the number 0 is going to be important as we interpret this. That 0 means no difference. So when we're looking for the confidence interval for the difference in the proportions, in order to interpret it, we want to see what numbers are captured within the lower bound and the upper bound. And we want to see if 0 is captured within that interval. If the interval contains 0, this is some evidence that the populations are equal. If the lower bound and the upper bound are both positive, that gives the indication then the first proportion that you used is greater than the second proportion that you used. Okay, they're greater. It's different. If the lower bound and the upper bound values are negative, that means that the first proportion that you used is less than the second proportion. Okay, so you're basically going to look at that interval and see, does my interval capture 0? If it does, there's no difference. If those values are greater than 0, both the upper bound and the lower bound are more than 0, so they're positive, then then your first proportion will be greater than your second one. If the opposite is true, if the lower bound and the upper bound values of your confidence interval are negative, then your first proportion is less than your second proportion. Now, I don't want you to get too caught up in the actual statistic for this, because if you look at this, all it's doing, let's look at the center part of the statistic right here. Okay, this center part looks familiar, doesn't it? If we just had this part of it right here, that is just the standard error formula. What they've done is it combined the two standard error formulas into one. Okay, that's all it's doing. So it's combining the two together. It's taking the square root once. For our situation, you will not have to calculate this by hand. We will only be using technology to figure this out. You will only need to interpret the interval to determine if there is a difference between the two populations, and if it's the first population is greater than the second, or if the first population is less than the second. All right, so let's try doing this from scratch. You're going to need the same necessary materials that we used in the last lecture. That means pencil or pen. You need paper. You need a calculator. You need a technology for the probability calculations. It will help if you have the confidence interval multipliers, and a probability diagram will probably be useful at this point. Okay, it says, in August 2014, the Pew poll asked random samples of 2,002 Americans, non-scientists, and 3,748 scientists if the space station had been a good investment for the U.S. Of the non-scientists polled, 64% said that the space station had been a good investment. Of the scientists polled, 68% said that the space station had been a good investment. Construct a 95% confidence interval for the difference between the population proportion of scientists and non-scientists who believe the space station had been a good investment for the U.S. Based on your confidence interval, is there a difference between the population proportions? Okay, so let's start by just kind of writing this out. So I'm going to go ahead and write non-scientists here. And over here I'm going to write scientists, right? And for the Americans that were non-scientists, they talked to 2,002 of them, and for the scientists, they talked to 3,748. And for the non-scientist, 64% said that the space station had been a good investment, and of the scientists, 68% said it had been. Okay, notice, doesn't say anything about this distribution being normal. So we got to check not just one of them, but we got to check both, because we need that to be in place for both. So I'm going to go ahead and scooch this up a little bit here. And I'm going to go ahead and check the central limit theorem for both. So here I'm going to do central limit theorem for both, CLT. I'll do random and independent. The scientists said they were randomly selected, So it doesn't talk about independence, but they did say that they were independent of one another, like the two samples weren't related. So that looks like it fits. The next one is sample size. We need both NP to be greater than or equal to 10, and we need the failures to be greater than or equal to 10. So here for non-scientists, I have 2002 multiplied by 0.64. And let me bring my calculator over. My Google calculator is right here. 2002 times 0.64 equals, I'm going to round it to 1,281 people. I'm going to round it to 1,281 people. Okay, rounded it to that. Is this number greater than or equal to 10? It is. That looks good. Now, these are my successes. Now I need the difference to be my failures. So I'm just going to do it 2002 times 1 minus 0.64. Okay, I'm just going to do it algebraically. Clear this out. 2002 times parenthesis 1 minus 0.64 close parenthesis equal, and I'm going to round it to 721. Is 721 greater than or equal to 10? It is. This checks out. Check. Okay, so this checked out. Now I have to do it again for the scientists. You have to do it for both. So we're going to go ahead and do it for the scientists. So this is going to be 378 times, so this is going to be 3,748 multiplied by 0.68. Why 0.68? Because this has a different proportion. So let's figure this out. I'm going to bring over my Google calculator, clear this out, make sure that I hit everything correctly. So 3,748 multiplied by 0.68, and I'm going to get 2,549. Is that number greater than or equal to 10? Yeah. Okay. This time I'm just going to take the difference. So I'm going to, it's the same thing. Remember, these are my successes, so my failures is going to be everything that's not a success. So let's clear this out. I'm going to take 3,748 minus 2,549. I get 1,199. So my failures are just 3,748 minus 2,549, and that's going to be 1,199, and that is going to be greater than or equal to 10, so that checks out too, and I can go here and check this out. Perfect. Next, I need my population size. Okay, we're talking about Americans. So I need my population to be greater than or equal to 10 times my sample size. So here, my sample size, I need my population, I need big N to be greater than or equal to 10 times 2002. So I need my population size to be bigger than 20,020. Are there more than 20,020 non-scientist Americans in the United States? Yep. And here, the same condition needs to be met. This has to be bigger than 10 times 3,748. So the population of Americans that are scientists needs to be bigger than 37,480, and that is true also. Okay, so the conditions of the central limit theorem meet in every sense of the word. One thing that I want to add here is not only do these samples need to be independently sampled, and we get that through SRS, but they also have to be independent of one another. So these are also independent of one another. Okay, so my conditions of the central limit theorem are met. There's another final piece of organization that I want to discuss. We're going to say that our non-scientists are going to be the first sample, and we're going to say that the scientists are the second sample. We will also need the number of successes as well. So here is the number 1,281 was the number of successes for non-scientists, and the number of successes for scientists is 2,549. So this is important before we go into StatCrunch. So here we are in StatCrunch. To get to the appropriate calculator, what we're going to do is we're going to go to Stats, go down to where it says Proportion Stats, go over where it says To Sample, and then finally click where it says With Summary. Okay? Then we're going to look at the information for sample 1 and then the information for sample 2, and then be able to just like put everything in there and calculate all our data. So let's look at the information for the sample 1. Sample 1 was non-scientists, and what we were able to calculate was there was 1,281 successes out of 2,002 observations. For the second sample, when we're talking about just scientists, there were 2,549 successes out of 3,748 observations. We want to click on where it says confidence interval for P1 minus P2 and put down that we want the 95% confidence interval level, and then we're going to go ahead and hit compute. Okay. What does this tell us? This gives us the lower limit and the upper limit right here. Notice both of these are negative. So what I've put here is just the same printout that I had from StatCrunch. So this is identical. I've gone ahead and added the information where it says non-scientists and scientists, so they're easy to discuss. And over here, I have added in larger font what the lower bound was and the upper bound was of the confidence interval. Notice, this is a negative number and this is a negative number. Okay, both of these values are negative. So, since they're both negative, they can't contain 0, right? 0 is greater than negative, so 0 is not contained within this interval. Both of the values are negative, so they can't be positive, so that's out. This says both of the values are negative. That means that the population proportions are different. That the proportion of people that are non-scientists that believe that the space station is a good idea is less than the proportion of the population that are scientists that believe the space station is a good idea. So notice here we had 2,002 people, right? And we had 3,748 scientists. Our sample sizes were different, but we're still able to compare the two. Just as in past videos, all the calculations are available here for you to review on the Google Slides that are linked below. Let's just do one more example on the interpretation of confidence intervals used to compare two populations. This one says, extracting natural gas through hydraulic fracturing or fracking is a controversial practice. Residents in 2 states with large natural gas deposits, Michigan and Pennsylvania, were polled by the University of Michigan to determine whether they favored or opposed fracking. Let P1 represent the proportion of Michigan residents who favor fracking, and P2 represent the proportion of Pennsylvania residents who favor fracking. A 95% confidence interval for the difference in the population proportions is negative 0.0184 as the lower bound and 0.117 as the upper bound. Does this interval indicate that there is a difference in support of fracking between these 2 states? What I've done here is I've just made things a little bit bigger, and I've gone ahead and put this interpretation table for us here. Let's look at the interval. The lower bound is negative. The upper bound is positive, which means that 0 is captured within that interval. The interval contains 0. What does 0 mean? No difference. So here, interval contains 0. That means there is no difference. The 2 populations are approximately equal. So, since the confidence interval contains 0, we can conclude that there's no real difference, no significant difference in the proportion of residents who support fracking in these 2 states. Now you might ask yourself, hey Torres, you never checked for the conditions. Well, we didn't have any numbers to check the conditions. So given that in this situation we were given the interval, we can only interpret what we have. I've gone ahead and written down all the conditions for you. Remember, if you're given the raw data, the raw summary, you need to go through the same conditions that you would for the central limit theorem, but you have to do it for both of the samples. So you're going to look for random and independent sampling. You're going to make sure that they both meet the condition of the large sample. You're going to check to make sure that they both meet the condition of a big population. And you're also going to check to see that the samples were drawn independent of one another, meaning that there's no relationship between the objects in one group and the objects in the other group. In order to do the calculations, you're going to use StatCrunch. If you want to use other proportion statistical software, you may. This one's just really super easy to use, and I use it a lot on my examples and probably on the exams for you to interpret output. And this gives you the information about how to use StatCrunch to figure this out for yourself. So what's the big idea? Today's big idea is that you can use the differences between the sample proportions to compare the differences between 2 population proportions. In order for this to happen, you need to make sure that all the conditions of the central limit theorem can apply so that you can make a reasonable estimate of the difference, or if a difference exists. When you interpret the confidence interval, you know that if 0 is contained within the range of the lower bound and the upper bound, then there is no statistical significant difference between the 2 population proportions. If both values are positive, that means your first proportion is different than your second proportion. The opposite is true. If you have both values that are negative, then the first proportion is significantly lower or less than the second proportion. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay? This is your teacher, Torres, saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!